Hello, everyone, and welcome to the webinar for today. We thank you for joining us. On behalf of the Research Committee, the Research and Industrial Relations Committee of the Auburn Research Advisory Board, welcome to today's webinar, which is the fifth in the series of our webinars featuring the cutting-edge research of Auburn University faculty researchers. Today, we have Dr. David Beverly with us, who will be speaking on GPS navigation and vehicle control at Auburn's Gav Lab. And David is a professor in the Department of Mechanical Engineering at Auburn University. He directs the university's GPS and Vehicle Dynamics Laboratory, otherwise known as Gav Lab, which focuses on the control and navigation of vehicles using GPS in conjunction with other sensors, such as inertial navigation system sensors. The Gav Lab's research thrusts are focused towards vehicle dynamics and transportation systems, including heavy trucks, passenger cars, off-road vehicles, as well as autonomous and unmanned vehicles. Dr. Beverly received his BS from Texas A&M University in 1995, his master's from Massachusetts Institute of Technology in 1997, and his PhD from Stanford in 2001, all in mechanical engineering. And now we'll just go through a few of our housekeeping items. The webinar is scheduled to last for approximately 1 hour. Dr. Beverly has a class to get to at 3, so we may try to end it just a little bit early. All of our webinar participants are initially on mute, so if you desire to ask a question, which Dr. Beverly will be happy to answer while he is speaking, if you have that ability, you're welcome to use the panel on the right-hand side of your screen and unmute yourself. We just ask that you mute back when you're finished. There will be a question and answer session at the end of the presentation. If you don't have ability to access the control panel or speak, you can send me and type me in the question panel any questions you may have, and I will moderate them and send them to Dr. Beverly. If you would like to share this webinar with your fellow workers, we will publish it on the Research Advisory Board website, which is located at the bottom of the screen, probably tomorrow. And if you want to share your webinar, you may do that. And if you know of people or organizations who have specific interest in the research topics that Dr. Beverly discusses today, you may contact him at that email address. And at the end of the webinar, there'll be a short survey which we'll email to you. And we ask you to complete that so we can make sure that we're living up to what your expectations. All right, I'm going to turn it over to Dr. Beverly right now. There you go.
Can you hear me, Vicki?
Yes, I can hear you.
Hopefully you can see my screen.
Yes.
All right. Well, good afternoon, everyone. Sorry, my voice is acting up today. I haven't even had class yet, so it's not from yelling at students. But so I will try to manage through this. Basically, I'm just going to go through and talk about a smorgasbord of things that we're doing in my lab, and just really kind of it's just going to maybe feel a little bit random, talking about just a bunch of the different projects that we're going through. But just want to give a flavor of the work that we do in the lab. And you'll see overall that most of the work basically revolves around navigation of vehicles. So kind of start off and just give a little bit of an introduction to my lab. We're currently 20 students. There's 8 PhDs, 10 masters, and 2 undergrads. Actually, I've hired 2 more undergrads, so I have 4 undergrads. So of those, 18 are actually now with the 2 additional undergrads, 20 of them are U.S. citizens. And that's kind of a really unique aspect, I think, in graduate schools. I didn't really realize how unique it was until several folks started commenting on it. And so, again, we run a very group of individuals, basically, that are doing work in some of them in sensitive areas. And so the fact that we have so many strong U.S. citizen students working in the lab, I think is an interest to a lot of people. In fact, several of them are even cleared. And I've been told many times that's probably my biggest asset is those guys in the lab. So they've past folks from my lab have gone on to be very successful. They're working at places like SAIC, Parsons, IS4S. Parsons has hired 7 in a row, I think, of my graduates. IS4S has 4. Dynetics has several. The lab runs about $600,000 a year of research, and that research comes from a variety of sponsors. So DoD, so Amerdex, CERDEC, TARDEC, MISIC are all sponsors. Small businesses, IS4S, Autonomous Solutions, Robotic Research. We do work with contractors, SAIC, Dynetics, Parsons, and then other groups such as the Federal Highway Administration. Actually, probably we just received a $1 million project with the Federal Highway Administration. So over the past 4 years, I think they've funded probably $2 or $3 million of our research. John Deere, Navcom, and Nissan also have been supported our group. As I mentioned, kind of our research thrust really broken down into 2 areas: navigation, and within navigation, we do a lot of work in GPS, but also GPS integrated with other sensors, so inertial perception, such as LiDAR and camera, and within that, sensor fusion and looking at different aiding techniques. And then kind of the other half of the GAB lab is the vehicle side, so looking at vehicle modeling, control. We've done things for OEMs such as vehicle handling and stability control research, and also anti-rollover kind of work. So in my lab, as I mentioned, we do a lot of navigation work and a lot of vehicle control work. And so we've worked on a variety of different platforms, so OEM cars such as the Infiniti G35, agriculture vehicles with John Deere, military vehicles. We were involved in future combat systems when that was around. You see a small ATV from the DARPA Grand Challenge work, and even some small PackBot type robots. And then, of course, the question is, what's the next vehicle we're going to work on? And so we've actually, in the past, and this has been getting a lot of publicity lately, we've done work with a autonomous canine. So the vet school trained a canine to be able to listen to commands, and we basically put a GPS receiver pack and a smart controller that we program to be able to send the dog to waypoints. So you can imagine things like you want to do border security or search and rescue or search an area remotely without an operator. You could use a device like this. So one of the other things that I'm really proud about our group is we don't do research just for doing research. So we are in an academic setting, but we're a very, very applied lab, and so really proud about the fact that a lot of our work gets integrated into systems. So when we were working with the FCS folks, a lot of our algorithms were being integrated into the autonomous navigation software with GDRS. Some of those algorithms now are being integrated into Lockheed Martin, into what was called the CAS program. It's now AMAS. And so they've taken our software and integrated it into their platforms. Some of our vehicle modeling has made it into different simulation environments. Deere is currently testing our control algorithms and basically forcing us to write them in a way that they can integrate them easily into their vehicles at future points. And even work that we've done with OEMs like Ford basically have taken our algorithms and at least tested them, so they're not necessarily inserted in current production vehicles, but they have tested them on their own vehicles. Some of the resources in our lab, so we have a variety of different GPS receivers, including just standard hardware GPS receivers, but we also have a lot of specialized software receivers. So we have a NordNav IF recorder and software receiver that lets us record L1 IF data. We can record that data and replay it through the receiver. We can replay it through our own. We have our own C and MATLAB software receiver algorithms that we can play that IF data through. We're also building up our own FPGA-based IF and IMU recorders so that the IMU and IF data is time synced. And then we've developed some FPGA reprogrammable GPS receivers and we're in the process of moving those to real time. And so that allows us, again, to be able to collect IF data, develop new tracking algorithms, and see how they perform in different environments, whether it be in noisy environments. We're actually going out, well, we're supposed to go out in 2 weeks to White Sands for what's called NavFest to collect data in different jamming environments. That currently is on hold due to the current government situation, so it may be rescheduled till December. But we'll take these IF recorders, we'll record data in those environments and process that data and look and see if we can develop algorithms that can improve their performance in various scenarios. We do some work with software-defined radios. In fact, we have some software-defined radios that we do GPS record and playback, so we can record a data signal and then we can play it back into different receivers and test performance. Inertial sensors, we have about every MEMS inertial sensor. We also have some automotive and tachover-grade inertial measurement units. We have a couple of test vehicles, the Infinity G35, a couple of by-wire ATVs, and a couple of SUVs. And then cameras, LiDARs. I don't know if you can see my mouse on the screen, but there's a LiDAR. Basically, it's made by Aveo, and it's actually about to be a production vehicle in 2015. And then below it's a small camera. It would be a production type level camera for doing lane tracking type work. And then for test facilities, we have a 1.7 mile oval test track, and we also have an off-road UGV course that's cut through the woods, which we actually use for a lot of harsh GPS data collection. So the heavy foliage simulates a noisy environment for testing GPS algorithms. So our positioning work basically can kind of be broken down into 3 main areas within this area of localization. So one area that we focus on is accurate and robust positioning by integrating sensors, whether it's cameras, IMUs, LiDARs, and we integrate them in loosely coupled, closely, tightly, and even deeply integrated systems. We have fault detection exclusion algorithms that we run on our GPS signal processing. And then we do work with relative positioning between vehicles. So whether we're trying to position a towed instrument package for doing looking for unexploded ordnances, or even in the agriculture environment where they're towing equipment. So we're doing precise positioning of both the vehicle and the towed equipment, or relative positioning between vehicles. And then even some environmental localization, such as simultaneous location and mapping, where you're looking for objects, mapping those objects, and then navigating off of those objects. So this is work that we're doing for GPS denied or GPS harsh or GPS limited environments. So one of the things that we're developing in the lab is what we call a GPS simulator. So on the market you can buy RF simulators. Our current this is not an RF simulator at present. It's what we call a GPS simulator because it simulates GPS outputs. So instead of providing RF outputs, it provides NEMA messages or range and pseudo-range measurements, just like a receiver would be. And so we use it in the lab for several of our programs where we want to basically simulate a different receiver that's hooked up to a module. And so within that, we have realistic acquisition times. We have noise values. We can put in building models, so we can look in a certain environment and say what satellites would be available this time of day at this location, given these buildings located around me. So you can put in 3D models of the environment and determine which satellites are available. And then we're in the process of trying to use one of these software-defined radios to see if we can take that and then actually turn it into a low-cost RF simulator. Amberdeck actually is interested in this for hardware-in-the-loop testing, and so we're in the process of seeing if we can turn this into this GPS simulator, run it through the USRP software-defined radio, and turn it into a low-cost RF simulator. And so that's current work in the process. This is just a snapshot of some of our GPS INS fault detection exclusion performance driving around Auburn University. We are driving in an area with a lot of tree cover around. And so you see on the left, you see the large jumps basically from the GPS measurement. And so what we do is we basically look at each pseudo-range or each signal to each satellite on an individual by individual basis. We compare it with what the IMU states the change in the current vehicle position is. And then if we see any large jumps on a single satellite measurement, we remove it from the solution and then do our integration. And so what you can see, it's a little more clear on the right. You see the red basically is GPS only with the large jumps. It's kind of a avocado green color is GPS INS. So if we took those GPS measurements with those large jumps and integrated it with the IMU, you still get small jumps. The IMU filters them somewhat, but you're still adding faulty measurements into that integration scheme. And then the cyan line is the GPS INS with the fault detection exclusion. So once we've removed each faulty satellite signal, then what we have. And so this is much better than, say, removing the entire GPS position solution. So you might be in an environment with 6 satellites. Maybe only one of the satellites has a faulty signal from the foliage or multipath. And so instead of removing the entire solution, you remove the one bad measurement. And so you're still able to use the 4 or 5 good measurements to reduce your IMU drift. And so you get kind of your optimal performance. Let's see. This is another program that we're doing for CERDEC, and this is in collaboration with a small company, IS4S, where we're looking at network-based navigation. And network-assisted GPS is pretty well known, but usually it relies on some infrastructure to broadcast the assistance data. And so what we're looking at for the Army is an application of peer-to-peer network-based assisted GPS. And so the idea is I have a set of dismount soldiers, maybe that are sweeping an area. And so I've got 8 or 9 soldiers on the ground running around and no infrastructure per se, and I want to communicate data between them that helps each of their positions. And so if I provide ephemeris data to each of those members of that squad, then they get rapid time to first fix and reacquisition. And then I can also broadcast differential information or GPS information so that I can get differential corrections so I can know where the other members of my squad are relative to me. And after the first year of this, we've tested it using the rifleman radio that you see there on the right. We basically did a demonstration, kind of a static demonstration with a couple of rifleman radios and some GPS receivers where we broadcast this data between the soldiers and show the improvement that you get by sharing GPS data. On the top is a test that we did here at Auburn University, and what we did here is we had one person walk out of the building. He's walking along the road and doesn't actually get any position data until the magenta line. But as soon as he gets some data, the GPS data is broadcast back through the radios back to another user. And so as soon as that user pops out of the building here, he immediately gets a position fix. And so you can kind of see the improvement from the network navigation. We've also been doing a lot of work on precise relative navigation. So you can imagine in applications such as the vehicle convoys or even refueling operations where you want very precise measurements between the vehicles. This was work that was actually originally developed for doing some unexploded ordnance or minesweeping operations where they had ground penetrating radars on 2 vehicles and had a very tight requirement on the positioning of those ground penetrating radars. And so we developed some relative positioning algorithms that use the GPS carrier measurements to get centimeter level relative positions of every vehicle around you. And it's a 3D position vector. So on the cartoon on the bottom is basically a drawing of how I could use this in automotive applications to be aware of my surroundings and where the vehicles are if I have a vehicle that's heading towards me, is that vehicle in my lane or in a different lane, and so on and so forth. So this slide here pretty much just says the exact same thing. So kind of the only interesting thing maybe is there on the bottom right. So this is some of the data from our algorithm running real time, and this is the algorithm actually that's been integrated into with Lockheed Martin into what was CAST and now is the AMAS system that was developed out of TARDEC to do these relative position measurements for a convoy of vehicles. And so we've tested this also here at Auburn University using a couple of our test vehicles. So you see here a lead vehicle, which is a Santa Fe. It's driven by a human. It has a GPS receiver on it and then a radio. Data is broadcast to a following vehicle. This is one of our by-wire vehicles, ATV. Takes that data, processes a relative vector between the leader and follower, integrates that also with an IMU that's located on there to allow automated path following. And so what you're going to see here is a test. These are two different tests run at two different camera angles. So there's a person in the following vehicle. That person in the following vehicle is controlling the throttle. So you can think of it as the person's controlling the following distance. And then the actual lateral control, the steering, is all being done autonomously based on these relative position algorithms to follow the vehicle path. And so the following distance can be automated as well. We have another program to look at that. But for this, we were really just looking at the path following capabilities. And so we'd have the driver control the throttle, but not the steering. So I'm going to actually bring this top left figure back again. You'll notice here where the Santa Fe crosses this path, kind of you can make a note for the location, and then you'll see the other vehicle will pass that same location. And we're not driving just directly to it, so we don't cut corners. We're following the path, so we keep a database of the past relative vectors between the vehicle. And as that vehicle passed by, hopefully you can see he had the laptop in his hands, but he wasn't controlling the steering. So yeah, the steering was completely automated. And I'll let the video continue to play out. On the right, you see some of the error data. Dark black is our navigation positional error. The gray is the following error. So the gray really is a combination of the black and then our control algorithm. And so the purpose of this really was the navigation aspect, so we didn't focus too much on really tightening down the actual control aspect. We really cared about what those dark black dots were doing. All right. Not sure how to make this go away. Vicki, is it on?
What are you trying to get to go away?
So on my screen, something popped up. Maybe it's not showing up on yours. The
No.
GoToWebinar thing popped up.
No, I don't see it on mine.
All right, I'll just ignore it. And
Yeah.
hopefully it's not covering up anything I need to see.
No, we don't see it. You're
All right. So moving on to some of our multi-sensor fusion for navigation, and this is work that we've been doing primarily for Federal Highway, but also has military aspects. And the idea is to fuse everything, all the sensors that are available on a vehicle in an intelligent way to improve the positioning robustness. And so vehicles that are coming off the OEM's markets right now, especially on the high-end vehicles, but it's going to start to find its way on lower-end vehicles, come with navigation systems, so that means they have a GPS receiver, come with electronic stability control. That's actually mandatory in the U.S. now, so that means there's some subset of inertial sensors, accelerometers and gyroscopes, and wheel odometry measurements. In the mid-range, you've got cameras that are doing lane tracking for lane departure warning, and then on some of the higher end ones you have the radars that are being used for the adaptive cruise control, or LiDAR for adaptive cruise control. And then you got V2V, vehicle-to-vehicle communication devices based on dedicated short-range communication, or what's DSRC. And so we looked at, can you integrate all these measurements together to improve your positioning performance? And one of the things that came out of that was the ability to do vehicle navigation with just 2 GPS satellites. So typically you require 4 GPS satellites to determine your position, but we showed that you could actually add a couple of constraints with a map database. You can add a vertical constraint with the camera that's looking at the lane markings, and that map database you add a lateral constraint. And so with those 2 constraints, now you can determine your position with just 2 GPS satellites, which is very beneficial in an urban environment where you have buildings blocking GPS satellites. We also put together a graphical user interface, and so this is going to be a video that shows that graphical user interface. We can actually run it real time, or we can take the data that we've collected to a database and then rerun it and change the algorithms and replay the data. And what you're going to see on the right is you see these kind of ghost vehicles. One is the RTK, which is the true position. One is a filtered position. One's a GPS only position. And then we can turn on and off different positioning. So as I run this, if it runs, on the top left is the view that the camera is seeing, or sorry, this is the camera algorithm that's tracking the lane marking. So this here in the middle is the actual view from the camera. So it's picking up this lane marking and then determining its position in the lane. Up here is some visual odometry that's running off of a stereo camera system. And then down here he tells you the number of GPS satellites that are in view, and then some information about the position. So I'll run this again so you can take a look. And one of the things that usually people see is there seems to be a latency between the filter solution and the RTK solution. And it's just the way we were fusing the data and the time sinks. So some data was on certain computers and some data on another computer. So some of that latency you see between those people as we drive on our test track is not true latency. It's just in the way that we've got the setup running. On our GPS signal processing, we've started doing a lot of work in deeply integrated GPS INS or vector tracking, where you're integrating all of the signal measurements in a single common filter. And so instead of having individual tracking loops, you now take all the correlator outputs and basically combine them in a single filter. You predict what those correlator outputs should be the next time step, and then look at the error between your prediction and the actual and correct based on that. The advantage is that it provides near instantaneous signal reacquisition after short GPS blockages. It also improves immunity, improved immunity to noise, i.e. jamming or foliage. And we've currently implemented on a FPGA, which is real-time capable. We don't currently have it real-time capable. We hope within the next year that'll be a real-time GPS vector tracking receiver. And then you can integrate other measurements in that, such as an IMU or the LiDAR and vision. And in the bottom right, you actually see the benefit through a heavy foliage environment. So the dots, the blue dots, are from a Novatel GPS receiver. And so you have several outages. And also you can see some jump points. The red is using the vector tracking algorithm, and so you get continuous coverage through this heavy foliage environment because of the ability to track weaker signals as well as reacquire signals after short outages. As I mentioned, we're trying to move that to real-time vector tracking, and so we've looked at a new I don't know if you want it to, basically it's an FPGA with an ARM processor called the Zinc board. And so the idea is we'll do the correlators on the FPGA, and then we'll do the sensor fusion common filter algorithm on the ARM processors. We're currently using an off-the-shelf wideband front end, but we're looking at making our own specialized narrowband RF front end, so a typical GPS front end as part of that. This is some work that we did for the Navy. They basically came to us because of our vehicle dynamic expertise and wanted to know if you could use some dynamic constraints to reduce the error growth from the inertial measurements, the IMU on a vehicle. So a lot of times there are vehicle constraints are made in the vehicle navigation that basically say the vehicle can't slide laterally. Another way to say that is so there's no lateral velocity, or the wheels don't slip laterally, or in vehicle terms it's known as side slip. And so what we did is we basically looked at different grades of IMUs and using vehicle models to see when that using that vehicle constraint was advantageous and when it was actually bad to do. And so we did a whole series of simulation tests. I'm just going to show one of the experimental tests where we took a vehicle. It had an HG IMU on it. We had RTK positions, GPS positions for our truth, but weren't used in the algorithm. So the algorithm was only using the IMU measurements and then using these vehicle dynamic constraints. And on the right, you can see the path that we drove. So we basically drove in a field, started here at the bottom left, drove up, kind of did a circle. And the reason for this circle is we did some pretty aggressive turns where the vehicle is generating 0.5, 0.6 Gs of lateral acceleration, so fairly aggressive turns. And it's actually sliding, generating 7 to 12 degrees of side slip. What you see here on the left is the position, the reference position is in black. And then we have the blue is what we call no constraint. So I don't use any vehicle dynamic constraint. I just take the IMU and integrate it. And what happens is when I get back to the end, I have this error from the drift in the IMU. I have what's called a hard constraint, which says I'm going to assume always the vehicle can't slide laterally. So I'm only going to assume that it moves in the forward direction, and so I only integrate the longitudinal accelerometer and the yaw gyro. And what happens is I get pretty good performance at first, and then you can see I make this first turn, and I start to get some error, and that error basically grows over time. And then we have what we call the soft constraint, which is, well, if the vehicle's driving straight, use the constraint that it doesn't move laterally. And when I'm turning, don't use that constraint because the vehicle can have some lateral velocity. On the plot on the right, you see the positional error growth. And so what's interesting is by applying that vehicle dynamic constraint, I actually get worse performance than if I just integrated the IMU open loop. But the best is if I apply this what we call soft constraint. So use the constraint when it's true, but don't use it when it's not. So we've also done some work in indoor navigation where we looked at mapping an environment and navigating without GPS using, as I mentioned earlier, simultaneous location and mapping. So we're using wheel encoders, a LiDAR, and an IMU. And we're driving this vehicle teleop, and the main focus of this work was actually to build a display for a user. So I'll run this video here in a minute, but in the bottom right is the view from the camera that's on the vehicle. And so a lot of times there's a single camera mounted on the front of the vehicle that an operator is having to drive the vehicle from. And in a lot of scenarios, it's advantageous to be able to generate kind of a different view, an overhead view, if you will. And so what we did with this work is as we're doing our mapping of the environment, we build that map into a database and then allow a user to use the database to generate virtual views from anywhere they want. And so if you can imagine when I'm going around a corner, if I'm trying to go around an obstacle and I want to know when I've cleared that obstacle, I can use the sensors on the vehicle to build a map of where that obstacle is and then allow the operator to view it from above, have a bird's eye view. Here on the right is just a camera of someone following the vehicle. So this would just to give you information about what the environment looks like. So again, the bottom right is the camera view that the operator would have with only the camera. This is the view of just someone following the vehicle. And then this is, on the left, is our generated view. And you'll see in a minute it'll go around the corner and the operator will actually kind of change his, turn that off. You'll see him change his perspective on how he wants to look at the environment that he's driving on. So there he's rotated it, kind of put the view to be a little bit above and back, and now he's rotated again, and now there's the bird's eye view. He's driving around the environment. So really still using our navigation research, but then using it basically to provide other enhanced capabilities. Talk a little bit more just vehicle dynamic work. We've done some vehicle work with Ford where we were estimating this parameter that I mentioned earlier called side slip, which is a critical parameter for electronic stability control systems, and it's simply a measure of how much lateral velocity you have at the vehicle. And what you see here is this is a double lane change maneuver. The black is the reference. It's a $30,000 system that Ford uses for their reference side slip. And then the pink lines is our algorithm using the onboard GPS receiver that's already on the vehicle, as well as the onboard electronic stability control IMU sensors. So in other words, for no added cost, we're getting the same performance in side slip measurement as their $30,000 reference unit that they use only for testing. And below is the side slip error. And then on the right, we also estimate the vehicle roll. And, so again, the pink or magenta line is our estimate using only onboard commercial, only the sensors that are on a production vehicle versus their reference system. And I always like to show, so this is a double lane change maneuver. This is kind of what it looks like. So this is our test track that I mentioned earlier. I'll play the video again so you can see that vehicle during an aggressive maneuver, sliding sideways. And so I get asked a lot of times where we get our professional drivers. And so that's one of the advantages of having 20 graduate students in the lab, is a little bit expendable, so you can have them go out and run some of these crazy tests. I'll kind of close with mention the DARPA Grand Challenge. This is pretty old work, but it really is a culmination of everything we do. So it involves navigation, sensor fusion, and vehicle control. And these are, if they'll play, these are just a couple of videos of our vehicles running. This is my last slide, so I think we've got a good 10 or 15 minutes. If there's any questions, I'll let the video on the right will play for about a minute or so. This is actually, on the right is video from the actual competition, the desert competition.
Does anyone have any questions for Dr. Beverly? All right. I think you've stumped them, David.
All right. There's all my contact information and the lab, and like I said, feel free to email me or get in touch with Vicki if you have any specific questions.
Thank you, Dr. Beverly, for your presentation, and I'd like to thank everyone for attending today's webinar. I'm happy to announce our next webinar will be held on November the 13th from 2 to 3. It will be featuring Bob Norton from our Open Source Intelligence Lab, and he'll be speaking on science and technology intelligence. So please join us for that, and I will send you a reminder of that, as well as a link to view all of the former webinars that we've had so far. Everyone have a good day. Thank you.